this assessment, we're asked to show the mechanism of the reduction of an anhydride with lithium aluminum hydride to give 2 molecules of the benzyl alcohol. Now, I've gone ahead and rewritten the molecule and abbreviated the benzene rings as pH for phenyl, just to shorten what we end up having to draw. I'll give you a warning, this mechanism is way more straightforward than it's going to look like at the end, so focus on what matches things we've studied previously. To start with, lithium aluminum hydride is a strong reducing agent, and anhydrides, the carbon is highly electrophilic. Anhydrides are the second most reactive carboxylic acid derivative. And so this reaction is going to start by H- attacking the carbon of the carbonyl. When it does that, that's going to push a pair of pi electrons onto the oxygen to give us a tetrahedral intermediate. We can draw the tetrahedral intermediate this way. And so here's our new carbon-hydrogen bond. At this point, just as we've done in all of these functional group interconversion reactions, our tetrahedral intermediate is going to collapse. These electrons come down to reform the pi bond and kick out the good leaving group. That's going to give us, I'm going to do this in 2 different ways. I'm going to show the acetate, or the benzoate, forming here. We'll come back and do stuff with that in just a second. But we're also going to get the aldehyde. Now, we learned previously that lithium aluminum hydride can reduce aldehydes. So if we've got more lithium aluminum hydride around, in fact, aldehydes are highly reactive with a strong reducing agent like lithium aluminum hydride. So we can show another molecule of hydride, of lithium aluminum hydride, attacking that aldehyde carbonyl, pushing the electrons up to give us this alkoxide. Now we've got 2 hydrogens added. We don't have to show those, but we'll show both of those just so we recognize that this carbon has now had 2 hydrides from lithium aluminum hydride added to it. This molecule, we don't think of as a tetrahedral intermediate because there's nothing that can leave. All that's going to happen with this is that we would protonate in the acid quench step to give us the first of the benzyl alcohols we're making. We formed the first equivalent of benzyl alcohol. How do we form the second? Well, to answer that question, we come back over to when this tetrahedral intermediate decomposed earlier. These electrons came down and kicked out this benzoate here. Now, this benzoate is probably going to be hanging out by the lithium carbocation. And recall that carboxylic acids, or carboxylates, can undergo further reduction with the alane that was produced in this first step. Let me explain what I mean by that. When the aluminum hydride gave up H-, we now have alane that is present. And this molecule, carboxylates, can react with alane where the pi electrons are donated to the aluminum and H- transfers to the carbon of the carbonyl. This should be reminiscent of the reaction of borane with an alkane. If we follow those arrows, what we end up with, we'll still draw the lithium hanging out by the oxygen. We can have this oxygen-carbon bond. There's our phenyl group. This oxygen will now be attached to aluminum, which has 2 hydrogens. And we've got our new hydride added. Now, this one forms in a little bit different way than was formed in the other carboxylic acid derivative reactions, but this is essentially a tetrahedral intermediate. And as a tetrahedral intermediate, these electrons, the negative charge on oxygen, these electrons can collapse down, reform the carbon-oxygen pi bond, and kick out this as our leaving group. Now, what will that end up making? We can take a shortcut here, because what that will make is a second equivalent of this aldehyde. And with that aldehyde in the presence of more of the aluminum hydride, we can reduce it to the alkoxide and then protonate to give the benzyl alcohol. Now, the only reason that worked is because this was a symmetrical anhydride and it saved us space. But the point here, this carboxylate gets reduced to make the aldehyde again, which is reduced a second time. Now we've rationalized how we form both equivalents of the benzyl alcohol.